Alessandra Giovagnoli from Bologna, and she'll talk about inference and ethics in clinical trials in the presence of covariates, and it should become interesting. Please.
First of all, I've been told that the only way to make myself heard, since the microphones are really not real microphones, is by shouting. So I hope you don't mind, but I'll try and shout as much as possible. Thank you to whoever it was who decided to invite me to this very, very interesting conference. Half of my talk has been given in the morning by other people, and I assume that the second half is also going to be given by somebody else. So I don't really have much to say, but I'll say it anyway. This is joint work with Alessandra Giovagnoli, who's a young co-worker at the University of Bologna. So every time I say we, it's not because I think I'm the queen. It's the two of us. We've heard this before. Clinical trials pose very difficult ethical problems because there is the care that the physician must pay towards the single patient, and there is also the interest in acquiring new information for which might be beneficial for future patients. So we've had this a lot. We've had this discussed before, so I won't go into it. In what I call the early days, I think a trial which was randomized was assumed to be ethical. I mean, that was the best thing you could do, therefore you were being ethical. And people still, in my country, talk about randomized clinical trials as the golden standard. So you can't do better. Then we've heard this morning a lot about randomization and balance. Balance, to me, is related to optimality in many cases. But there is also a discussion on this because some people talk about cosmetic balance. Balance is good, therefore we should do it. I think, okay. When I talk about randomization and balance, I've mentioned, of course, Inference bias co-design, which started it all. But I also want to talk about a little bit about what I have put down as the ABCD, which is a modified bias co-design I worked on together with my colleague. I'll tell you later why I want to talk about this. More recently, the ethical problem has been approached more directly, and I think Play the Winner was the first design that was suggested, which tried to skew the allocation towards the superior treatment in a very myopic way. You know, the Play the Winner means if a treatment is successful, play it again, you assign it again. And of course, it wasn't randomized, so they had to modify it to make it, to include randomization. I think the point of view, as you've heard this morning, the modern point of view is to treat the three problems separately, together, but as three separate problems. Ethical considerations, optimal inference, and randomization. We want it all. More and more one hears about adaptive designs as the answer. But first of all, let's agree on what adaptive means. I liked the definition that Barbara gave this morning, which was very appropriate. In the medical literature, adaptive or flexible means that you can change your design along the way. You redesign your experiment so long as the conditional probability of type 1 error doesn't increase. But you can do what you like. But here we mean something else, as Barbara pointed out. There's a rule. It's an adaptive rule that takes into account past information, but once we set the rule, that's it. We don't change the rule as we go along. Well, I will give a slightly more general definition of adaptive. It's not just the past data that we may want to use, in which case we talk about response adaptive. Also the past allocations, like in Inference biased coin design, and I've coined the expression, I don't think if anybody else uses it, design adaptive to mean this. And there are covariates, of course. We also want to allow for, it would be nice to talk about covariate adaptive. Unfortunately, covariate adaptive designs means something else. So now people talk about covariate adjusted response adaptive designs. And this has become known as CARA designs. Here's the outline of my talk. First of all, well, I like theorems. But I'm also a lazy person. So I think let's try and use the theorems we got already. So I will give the results in the absence of covariates and try and use, well, see how far the results can be used in the presence of covariates. The second part is very short because I haven't done much work on this. I'm just at the start. Okay, let's start with the more formal definition. I take the case of just 2 treatments. A lot extends to more than 2 treatments, but it complicates the notation. So let Z be the Q-dimensional vector of covariates for the ith patient, and we put delta I equals to 1 if the patient is allocated to the first treatment, otherwise 0. So we have a sequence of treatments allocation, a sequence of responses, and a sequence of covariate vectors. There is one condition. We only allow the patient's expected response, in a special case it's the probability of success, to depend on the treatment that he or she receives and on that patient's covariates. So this is not for the case when you allocate 2 treatments to the same patients because of possible carryover effects. This is different patients every time in the sequence. So, on the other hand, the randomization rule is adaptive, means that the probability of assigning T1 as the next treatment may depend on everything, may depend on past allocations, data, all the data up to now, and all the covariates, including the current patient's covariates. So this is a very general, well, it's the most general case, I think. Right. So the sort of clinical trials I have in mind are the, I suppose, phase 3 trials when the size is sufficiently large to think about asymptotics. And the proportion of allocations is, of course, a random variable because of the dependence on past data. We say that the design converges to a given target if this random variable converges to a number, a set proportion, almost surely. This is because I'm non-Bayesian, so I want it to be a number, but Bayesians allow this target to be a random variable as well. What are the models most widely used in this context? Well, we get a response Y, but really we have to model 2 potential responses. One in the case the patient receives the first treatment, one in the case it receives the second treatment. These are very simple but common models. In the case of a binary response, usually we just take the probability of success, also the logit, but logits are more used for when there are covariates, I think. In this simple case, there's no need really for logit. And for continuous response, usually a normal or either homoscedastic or heteroscedastic. Very briefly, because we've had this before, what are the main criteria for inference? Well, the power of a test, or test of equality of the two treatments usually, the variance of the estimated mean difference, or the determinant of the variance covariance of the estimators. So in what follows, I'm going to take one of these criteria as, generic as my criteria. For ethics, well, a lot of the literature concentrates on the first ethical purpose, aim, which is to minimize the total number of patients. In other words, a lot of the literature is on stopping rules, how to terminate the trial fairly soon, as soon as possible. But more recently, they have concentrated on minimizing the expected number of patients allocated to the inferior treatment, or minimizing the expected number of failures. These two objectives are related, and in fact, in a lot of cases, they are equivalent. You get one if you get the other. Now, suppose we are being non-sequential. We have a fixed sample experiment. Each of these criteria, and many more, would give rise to an ideal allocation. So let's talk about ideal allocations. The most common ones are balance, which does come from de-optimality in most cases, or very common is the Neyman's allocation. Neyman's allocation minimizes the variance of the difference and depends on the unknown parameters. Observe that in the homoscedastic case, the normal model also gives rise to balance as the optimal allocation. That's why balance is so, is required in most of the times. On the other hand, if you want to minimize the number of patients, expected number of patients exposed to the inferior treatment, and minimize the expected failures, then you would have to assign all the patients to the better treatment. Of course, you don't know what the better treatment is. This is a very strong requirement. A milder version of this is to allocate with a probability which is an increasing function of the difference. So when P1 is 0, P2 is 1, so the extreme case in which the first treatment always fails, you would have 0 there, slowly going up to 1 when the first treatment becomes better than the second. So this is what you find used. Okay, now as to convergence theorems. So I want to know if and when the design converges to a target which is desirable in some sets. This is a result that we found a few years back. There is a simple condition to check to see if the design converges. The condition is this. The probability I've got here is the allocation probability, is the probability of allocating the next treatment. And what I take is the Cesaro mean of all these probabilities. If the Cesaro mean converges to a number strictly between 0 and 1, then the design converges to the same proportion of allocations. The advantage of this rule is that it's fairly easy to check in most cases. So we know just from the randomization rule whether or not the design converges. And then apart from that, we've also got the following properties of the estimators. The estimates are strongly consistent, asymptotically normal, and we know the asymptotic variance. This is the theorem I was referring to this morning. We can actually calculate the asymptotic variance, which is not the same variance we would have in the case of a fixed sample size, because there's more variance coming from the design itself. There's an extra variability. Okay, so we can apply the theorem to a lot of known cases and get get convergence. Play the winner. I wanted to mention this because the target, I mean, this has been known. We don't have to prove anything. Play the winner and all the randomized versions converge to the same target. Unfortunately, the target is not very good because we can show that this target is dominated by some other targets. In other words, you can find a target which is better both from the inferential point of view and also from the ethical point of view. Therefore, play the winner seems really a bit too myopic, short-sighted. Oh, okay. Now, suppose we really want to be strongly ethical and our target is 0, 1, the 0, 1. So we want to end up by assigning all the patients to the better treatment. There are designs that do that now, but these are very appealing, but they may be unsuitable for instance since the allocation tend to be strongly unbalanced, because these designs do not worry about the inference at all. They just worry about doing what's best for the patients. But of course, if we're experimenting, it's because we want to find something about both treatments. And so there is a conflict, of course. Now, sequential maximum likelihood, in a way, is the most natural thing you can think of. You start with a few observations and have a sort of temporary estimate of the parameters. And then, because you have an estimate of the unknown parameters, you have an estimate of the unknown target. And at that point, you can allocate with the probability equal to the estimated target and repeat the sequence. If you do that, well, the design converges to the target. So this is a way of going towards your target, and it's a fairly simple way. It's slow. It's slow. It doesn't converge very fast. The interesting result to me is the following. If the target is locally optimal, so we got this target to, from a criterion applied in a fixed sample size situation. If it's optimal, locally optimal in that sense, then is also optimal for unconditional inference. In other words, taking into account the fact that the design is sequential. So the design is good for, in this case too, it's a good design. There are more convergence theorems, like this one, due to Hu and Zhang. But personally, I don't know, I still have to persuade myself that we really need a theorem that tells us how the design is going to behave asymptotically, the design. I think we need the estimators. That's what we need. That's what we want. To know that the design is asymptotically optimal, normal, I don't know if that's very informative, but maybe I'm being stupid. Now, let's go back to the ethical purpose. So now suppose we choose two measures, one for information and one for ethics. And the main problem is, how do we put them together? How do we compromise between these two different aims? The final design will be randomized in any case. So there will be some randomization. We don't have to worry about that. We worry about the first two issues. The idea is to take some sort of mixture with some weights. Well, a very simple example is this. We get the two ideal allocations, different, two designs converging to the two allocations, and then take a weighted average or something. So we could have a biased coin favoring the better performer so far, favoring, which is more or less what some of the designs that we've been introduced to. I want to talk about this example, which is more interesting because that's where I got the idea for the proposal that I'm going to put forward. So we give weight lambda to ethics, 1 minus lambda to information. We choose two allocation probabilities, one which is decreasing with respect to imbalance, and one which is increasing with respect to the difference. So these are two ideas already existing in the literature, but they've been looked at separately as two separate issues. And these people, Geraldus, Melfi, Page, and Zhang, put it together by means of one compound allocation. So it's a mixture of two probabilities, it's a probability. And it can be shown that this converges to the unique solution of this equation. So they achieve the purpose, so to speak. Notice that they choose imbalance, so presumably the criterion they have in mind is some sort of de-optimality. There's another way of doing it by, instead of taking a mixture of the designs, taking a mixture of the targets and then converging to it. I don't think this is a very good idea, to be honest, because the mixture of two optimal targets can be very suboptimal. So what I suggest instead, what we suggest is to trade off the criteria, to mix the criteria, and then find a design that converges to the new target. So we get a new criterion and then a new target. Right, and so skip this. The weights. What weights? We think the weights should depend on the absolute value of the difference of the two probabilities, because so the weights become adaptive as well as the rest. They change during the course of the experiment. And by doing this, we get all sorts of nice results because we reapply the theorems obtained before, and we can actually say what the asymptotic properties of this design are. I said I was going to talk about covariates. I've only got 5 minutes left. Good, that's good. Okay, the problem is very complicated. Somebody has pointed that out this morning. Because the response can be binary or continuous, the covariates can be discrete or continuous, then there could be or not be treatment covariate interactions among covariates. So all sorts of combinations to look at, and some of those have already been looked at. I want to go back to the adaptive biased coin design for one reason. It came as a surprise to me, but not very long ago I received an email from the oncological unit, Brussels University Hospital, somebody who said they were wondering. They tried Efferent's bias con design and the Simon Pocock's version of it, which is for covariates. It didn't work very well. They thought the adjustable bias con design was very interesting. They tried it. It's less biased. It's got less selection bias, and therefore they wondered if it could be used in a covariate context. So my co-worker and I started thinking about it. We come up with some ideas. First of all, what is the ABCD? You take a decreasing function like this. This is what we suggest, but you can take it differently. And you allocate the new treatment according to this probability, to the probability, to this function applied to the imbalance. So it's a decreasing probability, so that the underrepresented treatment is a better choice being selected. Can this work with covariates as well? Well, let's be quick. Yes, we think it can be applied to strata imbalance. In other words, we have covariates, assume the covariates interact. So for each combination of covariates, we got a stratum, and we apply our rule to the imbalance in that stratum. So we make a randomized assignment according to this probability. The interesting thing is that if we use the same function, f, for all the design, then we have the same, the nice properties of the ABCD design are that the asymptotic properties are based on Markov chains. So you know a lot about this because they come from properties of Markov chains. So you apply the well-known theorems for Markov chains. And also it converges very quickly. So it's the design has got small sample properties that are good because it gets there very quickly. If we do this, we get the same property, the same Markov chains for each covariate. So there is balance on each covariate. And we think we can choose different Fs to reflect also relative weight to covariates, which is what people like to do. Skip this, and my conclusions are more research needed, especially in combining different criteria. I think that's the interesting point. How to put together something which is ethical in an ethical aim with an inferential aim. But everybody knows that's important.
Yeah. Comments, questions? Okay. So you're talking about asymptotic results, but as I understand, one of the issues of like Earn designs is always that you're guaranteed a limit, but we might never realistically hit the limit in small sample sizes. Do you have any suggestion on any thoughts on that?
Yes, restrict randomization. I mean, the less you randomize, the better. So, you know, if you can restrict your randomization.
In your last idea there, you suggested balance with respect to stratum. Does that suggest you're thinking of covariates that are factors? What about continuous covariates? Would you categorize?
Well, we've done some work. In some cases, we can do it with continuous covariates. So I can't commit myself to saying more. It hasn't been written up. Let's put it this way: the first part of the paper has been written up, but the second part not yet. So. Yes, I think we have some results for continuous covariates, but It's based on the theorem here. This, you see, when we find a target, we find a target which depends, because we have compromise criterion, we manage somehow to find an optimal target, which depends on the covariates, and then we implement it by maximum likelihood, by this recursive maximum likelihood, and because there are theorems that ensure the optimality of this type of design, we think that those theorems apply in our case as well. I would like to check it a bit more before saying it officially. We think it works.
There are no other comments, then thank you again.